All right, we'll continue our discussion. We talked about mean, median mode, variance, covariance. Okay, and I just missed one thing. It's called correlation. It's very related to variance. Correlation, you would have seen it using a symbol called rho or something like correlation coefficient, which represents the strength of correlation. Covariance talks about how much x varies with y, okay, the proportion of it, and correlation tells you whether it is correlated yes or no, okay, as a number, and it also tells you whether what's the strength of it, okay. In this case, it's positively correlated, which means that both are like if x is minus 1, y is minus 1, if x is 0, y is 0, if x is 1, y is 1. So it's positively correlated. Okay, so that's this. If you find the correlation coefficient of this line, it will be 1. Okay, and if you find the correlation coefficient of this line, it will be minus 1. Okay, that is the strength of it. It's like the maximum correlation you can get is 1, I mean, positive correlation you'll get is 1. Then the maximum negative correlation you will get is minus 1. So if it's, in this case, if x is minus 1, y is 1. Okay, and when x is 1, y is minus 1. Okay, so in this case, it's negatively correlated. So this is the formula. X, like you will have like x minus x bar. It is the same thing. X minus mu, x bar is mu. Okay, and y minus mu. Okay, and you have summation of it. And here it is like square root of summation of x minus mu whole square and y minus mu the whole square. Okay, x bar and mu. If it is a sample, it's x bar. If it is population, it's mu. Okay, this is the formula for correlation coefficient. So yeah, it talks about the strength. This is positively correlated. The strength is plus 1. Negatively correlated. The strength is minus 1. Okay, this is the one additional information. So we talk about mean, median, mode, variance, covariance, correlation, covariance matrix. I think this is sufficient to understand the picture of data. Okay. Now we'll continue with the probabilities. Okay. Let me erase this and we'll continue. We'll talk about variables and random variables. Okay, what is a variable? Okay, variable x is equal to 1. This is a variable used in algebra or programming. Okay, if you add x can take the value 2. If you try to assign it back, the value can change. So this is a variable because the value can change. So what is a random variable? Random variable you represent it as x actually, and it tells you the outcome of a probabilistic event. Okay, so let's say I wanted to find the probability of rolling a die. Okay, this is rolling a die. Okay, and I just roll it, and I get 2. Okay, now if I get 2, the probability of getting 2. Okay, this is a random variable because every time there is a random process involved in it. Okay, so I can next time when I roll it, I can get 6. Okay, so probability of the random variable getting 6. So in this case, the probability of since this is a fair die, okay, any probabilities is equal between 1 to 6. The probability of getting x is equal to 2 is 1 by 6, y is equal to 2, x is equal to 6 is also 1 by 6 because it's like uniform. Okay, there is no bias in this. Anything can come. So normally we represent random variable with the capital X, and you will probably something like x is equal to x, which means that the probability of obtaining the value, this is the value x is equal to 2 or x is equal to 6. Okay, and this is the random variable. So you can consider this as a function where you take a random process as an input and you get a probability as output. Okay, so it could be probability distribution. So the probability of getting any number between 1 to 6 in a die is this actually. So probability of this is the probability of die. So similarly, if it is a probability of getting random variable x, can take the value x for this can be like 1 by 2 for a coin toss. Okay, here probability of the random variable x is equal to like heads is equal to 1 by 2, or probability of random variable x is equal to tails. Okay, this is heads, this is tails. This again is equal to 1 by 2. So we're trying to convert a random process like this. Okay, which is I mean, you cannot deterministically tell what is the probability of this outcome. There is a random process to it, so you kind of do a the outcome is random, and you put the random value here, and you get the probability. Okay, this is the example of a random variable. Okay, now we'll talk about probability distributions. Okay, so if it is the, if the values are, discrete, like 1, 2, and 3, if you can count it, we use discrete probability distribution. If it is continuous, like heights, like 122.2 centimeter or 160.6 centimeters, and if it's half decimal points, that is a continuous values. This is called continuous distribution. So there are two ways. Most of the data you can represent either in discrete distribution or continuous distribution. So first, let's understand what is the probability distribution. So in this case, I told the probability of the outcome of any number coming rolling a die is 1/6. So in this case, what happens is the probability of the probability of getting 1 is equal to 1/6, 2 is 1/6, 3 is 1/6. So if you try to plot, okay, what is the probability of getting 1, 2, 3, 4, 5, and 6? It is all like 1/6. Okay, and this is 1/6. This is 1/6. So if you try to plot it, okay, and this is like, and if you try to see the distribution of it, it is all uniform. Okay, which means that if we sum all the probabilities of 1/6 to 1/6 to 1/6, 1/6, 1/6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, so if you try to sum all these probabilities, you will get 1. Okay, that's the rule of probability. So you can get the summary of, the summation of all the probabilities should end up as 1. And this is the probability value, like 1/6 is the number. Okay, and if you just have 1 all in the die, okay, in all the places, okay, and the probability of getting 1, if you have like the 6-sided die and everywhere it is just 1, the probability of getting 1 is 100%, right? It's like everywhere it is 6. So the probability here it will be 1 in this case. And probability of getting 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, and everything will be 0. Okay, which means that there is no probability of getting anything other than 1. So that's how we find the difference between this distribution and this distribution. This is a this is a uniform distribution where everything has equal chances. This is a non-uniform distribution where just having one value has a 100% chance and rest of it has no chance, because this is a die which has got 1 in all the sides. Okay. Now let's take one more example. Okay. Let's assume that I have a cake like this. Okay, and the cake is made up of chocolate in this side and vanilla flavor in this side. So half side is chocolate and half side is vanilla. If I just close my eyes and randomly touch it, I will be taking some, let's say I take a piece of cake and I just taste it. Okay, so what is the chance that it will be vanilla? Actually, this is chocolate and this is vanilla. Okay. Chocolate and vanilla. So if I randomly close my eyes and touch the cake, I can get a piece of chocolate cake. Again, if I close it and I can touch it here, I can get a piece of vanilla cake. So suppose somebody rotates the cake without, I have seen the cake, so I can randomly touch in the left or right. Suppose somebody kind of changes the orientation of the cake, and if I randomly touch it, again there are chances that 50-50. Okay, 50-50 of getting a piece of cake in either of the side. So the probability distribution here is 1/2, just like the coin toss. Okay, the probability is distributed between these two. Suppose the same cake, you have the same cake out of which 80% of it is made up of chocolate and just 20% is made with vanilla. Okay, like this is like 80% and this is 20%. Okay, and if I randomly close my eyes and just touch, and mostly I will be touching in the place where it is chocolate most of the time, and there are chances that I will touch the vanilla as well, so that I get a piece of it. So the probability of getting chocolate is higher, the probability of getting vanilla is lower. So this is an example of a probability distribution where it is not uniform. Okay, here it is uniform, here it is not uniform. So it is like the one is high, okay, and one is low, and this is chocolate and this is vanilla, and this is the probability distribution. Like this is like 0.8, 0.8, and this is like 0.2. Okay, and if I sum these two, again I will get 1. Okay, so this is how we can distribute it. Suppose if we have cakes of multiple flavors, okay, like hundreds of flavors, the probability kind of gets distributed between all of it, and you will get a probability which is a probability distribution function which is different from this, but giving equal share to it. Again, if you sum everything together, it will be 1. Okay, so 80% is nothing but 0.8, 20% will be zero point 0.2. Okay, and if it is if we divide into another, I mean like let's say 3 pieces. Let's say it is like 0.3, it is 0.4, and this is like 0.7, and this is like 0.3. So it's going to be 0.5, 0.4, and it's going to be 0.2. So the probability distribution changes. So based upon the, we have one more flavor added. Okay, so it's like chocolate, vanilla, and probably this is like a strawberry. Okay, so this is how the probabilities gets distributed, and the probability distribution gets changes. And all this are a kind of I mean, this is an example of a continuous distribution where I can exactly I can have variation in the cuts, okay, between these two. Okay, but in case of let's say randomly pick heights of students in a class. It could be like 166.2 centimeter, 166.3 centimeters. So this values are continuous. So in that case, I cannot represent it using bars. I represent it using a kind of distribution which is like this, where I can take the area between these two, okay, and get the probability of getting touching it. Suppose if I wanted to find the probability of getting a height between 166.2 to 166.7, then the area between this curve, okay, that helps us to assume that it is a cake, and this piece of the cake has got all the mass of this data, so that if I randomly close my eyes and touch somewhere, I might touch here and here, and the probabilities, if I touch it here, then I get that's the probability of getting this data. Okay, so this is how you find it, and if you remember integration in our videos, the area between these two, okay, between the limits this point and this point, if you kind of integrate it, it will give you the probability. Here we are able to directly get it from the bars. Okay, it is like 0.8 or 0.2. Here you cannot get it like for individual numbers. You can get it for the range of values. Okay, that's how a continuous distribution varies from a discrete distribution. Okay, now let's extend this idea of probability distributions. Okay, and see how we can make use of it in kind of some examples. Let's say we have Netflix as a movie provider, okay, and they have got let's say 100 users, okay. The 100 users is divided into I mean like they have like 50 like 50 male, female, okay, and they have like two movies, okay. One is called Titanic, okay, another one is called Jurassic Park, okay. The two movies, Titanic and Jurassic Park, and they have I mean like subscribers, like 100 subscribers in total. So we wanted to find out the probability distribution of the people who watch this movies. Okay, so the total number of people who watch the movies is 100. Okay, so the total distribution should be 100. Okay, and this is what this 100 means. And let's say we have 60 male and 40. Sorry, let me erase this and come back actually. Yeah, let's continue. We have a total of 100 subscribers. 20 of them are male, 40 of them are, sorry, 20 of them are male who have watched Titanic. Okay, 40 of them are female who have watched Titanic. Okay, so there are total 60 people who have watched the movie Titanic. Okay, let's say we have around 30 people who are male who have watched Jurassic Park, and 40, like let's say 10 people who are female has watched Jurassic Park. So it is like 40. So this is this total sum of 100 subscribers, out of which we have like say 50 male and 50 female, and this is the total. Okay, this is the total data we have. Okay, this is the total data we have. where we have again I repeat, the Netflix has got 100 subscribers, and this is the total number of subscribers. Out of which we have 50 males and 50 females, and 50 female, and we have two movies okay to watch, and 20 of the male have watched Titanic, 40 of them are female has watched Titanic. Okay, and the same way 30 years Jurassic Park was made, and then this is the data. Okay, and this is the data, typical data you will have, and we need to find the probability distribution of this data. Okay, so just like we had one piece of cake, this is like one piece of data we have. Okay, then we wanted to find the distribution of it. Okay, now how do you find the distribution? If you divide each of the boxes with the total, you will get the distribution of the share of that box with the total. Okay, which means that suppose there are like this is the male, okay, and this is female, okay, and you can see here there are about 20 males, 20 male who have watched Titanic, okay, out of 100. So which means that if it is Titanic, the Titanic, let's say Titanic, okay, 20 out of 100 watched it, so it's 0.2. 40 out of 100 watched it, so 0.4. Okay, and 30 out of 100 has watched Jurassic Park. Okay, let's say Jurassic Park. So I'll just put JP. JP for Jurassic Park. Jurassic Park, 30 of them has watched, so it's 0.3. Okay, and 10 of them have watched, 10 of the females have watched Jurassic Park, it is like 0.1. Okay, now if you see here, I have taken the total number of people and the movies, say like 40, 60, 70, 80, 90, 100. So this is the total number of population of the people. Okay, and if you see here, there are only two movies, and out of which they have distributed their preferences with these two movies. So if you see here, 20% of them was Titanic, of the male has watched Titanic, 40% of the female has watched Titanic. So if you sum all this, it becomes 1. So 0.3 to 0.5, 3 plus 2, 5, 0.5 plus 0.4, it's 0.9, 0.9 plus 1, it is 1. So this is the joint probability distribution of all the of this table. So together, if you have two movies and have 100 people, this is the joint probability distribution of how they share. Just like they share the piece of cake, this is how they share the piece of movies among themselves. Okay. So now, if you try to this is what we call it as joint probability distribution. Okay, joint probability distribution table. Okay, this is the joint probability distribution table. If you look at this, we focus on this box. Okay, this box is joint probability distribution table. Now, if you want to find, I mean, like, I don't care about whether they are male or female. I just wanted to find out what is the total number of people who have watched Titanic, and what is the proportion of people who have watched Titanic. Then it is called marginal probability, which means that I don't care about whether it was watched male or female. I just wanted to find out whether they watched Titanic or not. So then it becomes marginal probability. The marginal probability of Titanic is the sum of these two is 0.6. Okay. Okay, and the same thing. If you look at the marginal probability of Jurassic Park, I don't care about whether it was male or female. I just wanted to find out what proportion of people who watched Jurassic Park. It will be like 0.4. This plus this. So if you see the marginal probabilities of the movies, these two sum up to 1. So just notice the difference. The joint probability of all four sum up to 1, and the marginal probability of these two sum up to 1. So this is like I'm marginalizing the gender, which means that I don't care about the male or female. I just care about the movie Titanic, and I wanted to find the proportion of people who watched it. I just care about the movie Jurassic Park and the proportion of the people who watched it. Now you can flip the coin other way around. Okay, I am Netflix. Like a provider, and I wanted to find out. I don't care about which movie people watches. I just wanted to find the proportion of my subscribers. Okay, who are watching my movies. Okay, from their point of view, it will be like they're interested in the proportion of the people. So in this case, I'll just sum these two, it becomes sum the proportion of male, 0.3 plus 0.2. And similarly, the proportion of female, if it's like 0.4 plus 0.1, it's 0.5. So if you see again here, these two sum up to 1. Okay, and these two sum up to 1. So these are called marginal probabilities, where I don't care about the rest of the stuff. I can marginalize one and I can look into the other. Okay, so in this case, in the first case, I marginalized. I don't care about whether they're male or female. I just look into the prevalence of the movies. So these two are marginal probabilities. These two sum up to 1, and for Titanic it is 0.6, and Jurassic Park it's 0.4. And I get to the other way around. I just don't care about whether they are what kind of movie they watch. I just wanted to find out the probability. I mean the proportion of male in my subscription list. So I sum this. It's 0.5. Similarly, I don't care about what movie preferences they have. I just wanted to find out the proportion of female. I sum this. It's like 0.4 plus 1, 0.5. So these two marginal probabilities sum to 1 individually, and the joint probabilities sum to 1 together. Okay, that's the difference you should notice. Okay, if you try to add all, both the marginal probabilities, it will become 2. Okay, that's not how marginal probability works. It just looks into you can marginalize one and ignore the other. So in this case, in this joint probability, we take care of all combinations. So that's the difference between joint and marginal probabilities. Okay, now let's if you wanted to answer any of the probabilistic question, if you're able to generate this this table, okay, you just joint probability distribution table, you will be able to generate the marginal distribution. You will be able to generate everything. So practically generating this table is very difficult, because you want the examples are not that simple that you can kind of calculate and divide and create a distribution. That's where complex, it requires a lot of computation and power, and the number of variables gets larger, and this probability distribution table gets very difficult to compute. That is where you have a lot of sampling methods like Monte Carlo samplings and things like that to kind of estimate these probabilities. There's practical difficulties in implementation to get this sweet box like this, but assuming that we get it, we can answer most of the questions. So let's just not worry about the computation and how practically these are implemented right now. Let's focus on what can be done with the data. Okay, so now it helps to answer a lot of questions. So for example, if you wanted to find out certain questions, like, okay, let me erase this, and let's put some questions here. You got the point, right? This is the total data, and this is the probability distribution. Okay, and this is the marginal probabilities. This is the marginal probability. This is the marginal probability. Two marginal probabilities, and this is giant probability distribution. Okay. Just take a note that I'll erase this piece. Okay. So, okay. Now, if I wanted to find out some questions like, what is the probability of female? What is the probability of female? A simple question. Okay, what's the probability of the female? Which means that I'm asking a marginal probability question. So, what is the probability of the female who is subscribed is? You can take this sum of this. It's like 0.5. Okay. What is the probability of male? Again, it's a marginal probability question. Of a subscription, it is like 0.5. So I can ask the same question, like, what is the marginal probability of Titanic? People who watch Titanic, it is 0.6 and 0.4. Now let's get a little bit interesting. So I can ask the question like the joint probability. Okay, what is the probability of being a female? Okay, and watching Titanic. Okay, what is the probability of my subscriber being a female and she is interested in Titanic? So that's a joint probability distribution. So that's a joint probability distribution between Titanic and female. So this is 0.4. Okay, this is 0.4. So this is the box actually. So look at the intersection of Titanic. This is and look at the intersection of Titanic and female. You get this 0.4. Okay, this is what we call it as probability of A and B. Okay, and this is the joint probability distribution. Okay. And if you wanted to find, find something like What is the okay, given, okay, let's move little further. And let's say I wanted to find the probability of being a female or watching the movie Titanic. Okay, this is a different question. This is and, this is or. So if you wanted to find the probability of finding the female or Titanic, I sum up all the probabilities of female. Okay, that's 0.4, then 0.1. Okay, and the probability of Titanic. This is here. Sorry, probability of, one second. Female or Titanic, right? Okay, it's like 0.4 plus 0.1 plus Titanic is 0.4, 0.6. Okay, so this is like these three. Okay, 0.4, 0.1 plus 0.6. Okay, 0.4 plus 0.1 plus 0.45. There's a mistake. One second, let me check it. Yeah, we'll continue. Nothing wrong here, just small correction. So the question is like probability of female or Titanic. So what we should do is we should take into consideration the probability of female, that is 0.4 plus 0.1, that is 0.4. Okay, this is 0.4 plus 0.1 and 0.2. Okay, male, female or Titanic, right? So it's like this. 4, 5, 6, 7. So these three probabilities, 0.1 plus 0.4 plus 0.1 plus 0.2 for Titanic. So these three boxes, being female or Titanic. Okay, so it is like 0.233. So it is like 0.7, right? 4, 5, 6, 7. So if you go by the formula, okay, it is like the probability of this is like A union B. Okay, it's A or B, right? A union B is equal to probability of A plus probability of B minus probability of A intersection B. Okay, you can check this formula also. What is A? Probability of female. What is B? Probability of Titanic. Okay, so what is probability of A? That is what is probability of female? Is the marginal probability 0.5. Okay, and what is the probability of B? That is probability of Titanic. That is my marginal probability 0.6. Okay, that's minus what is the probability of being intersection of both male and Titanic. Sorry, female and Titanic. Female and Titanic is 0.4. Okay, if you look at this, it will become like 6 plus 5, 11. 11 minus 4. Okay, it will be 6 plus 11 minus 4. Okay. So, okay. 11 minus 4 is 0.7. So the same answer. Okay. 0.4 plus 0.1 plus 0.2. If you add these three two, I mean, like you will get 0.7. If you use formula, you will get this. So we have used conditions. I mean, you use this table and we are able to answer these questions. Let's answer a few more questions. Okay. Let me erase this. Okay. Let me also erase this. Okay, let's answer a couple of more questions. We call it as conditional probability. Probability of A given B is equal to probability of A and B. Okay, and this is probability of B. Okay, this is the definition for conditional probability, which means that given a condition, what is the probability of getting that? Okay, so let's take an example. So let's take given a condition. A condition is like given. Let's take given that somebody is a female. What is the probability of they watching Titanic? Okay, given that somebody is female, what is the probability that they will watch the movie Titanic? Okay, we will try to find out. Okay, and you can use this formula. Probability of A intersection B. Okay, probability of people who watched both Titanic and female, it is like 0.4. Okay, divided by the probability of marginal probability of B, marginal probability of female. Marginal probability of female is 0.5. Okay, so which means that 80% of the people, or 0.8 is the, I mean, like 80% is the chances that if you are a female, you would like Titanic, you would watch Titanic. Okay, that's the example of conditional probability. Okay, now let's take a couple of more examples. Given that you are a female, okay, what is that you the chances of watching Jurassic Park? Okay, the same question, okay, but in a different for a different movie. Okay, we will see. Okay, probability of A and B. That is probability of watching both the Jurassic Park and being a female. Jurassic Park and being a female is 0.1. Okay, and what is the probability of female? It is like 0.5. Okay, 0.1 and 0.1 by 0.5. So there are only 10% chance that you will be watching. So 20% chance that you will be watching Jurassic Park if you are female. If you see your total sum, it is like 80 plus 20, 100% of the female. This is split between two movies, Titanic and Jurassic Park, but the preference is more towards Titanic than Jurassic Park. This is an example of how you can use conditional probability to kind of answer these questions. Let's take a couple of more examples. Okay, so let's just make this a little bit more clear. Okay. Let's take an example like this. Okay, given that somebody has watched Jurassic Park, we just flip the coin. Okay, given that somebody has watched Jurassic Park, what is the probability that they are male? Okay, so again we can use the same logic. Okay, given that somebody has watched Jurassic Park, which means probability of marginal probability of Jurassic Park, okay, is 0.4. Okay. What is that they are being made? Okay, so we need to find out the proportion between male and Jurassic Park. Jurassic Park, the marginal probability is 0.4, and yeah, this is male and Jurassic Park. Okay, so it means the probability of male and Jurassic Park. Okay. Given that okay, A and B, so this is 0.3. So they should be male and they should have watched Jurassic Park. It is like 0.3 by 0.4. So it's like 3/4 of the people, or like 70% of the people who have watched Jurassic Park are actually male. So this you can answer this question in the reverse order as well. So this is an example of how you can use the joint probability distribution table. Okay, to answer questions which can be useful to make some decisions like the condition probabilities, marginal probabilities, and things like that. Okay, so this is the overall use of finding the joint probability distribution or probability distribution in general. You can answer a lot of questions. Okay. Hope this gave intuition. And a couple of more things to notice. If two events are independent, let's say probability of male and the probability of Jurassic Park are independent, which means that these two events are independent of each other. Okay, sorry, if probability of let's say a male, okay, watching Jurassic Park, okay, male and Jurassic Park, okay, if they are independent of each other, which means that there is no relationship with these two, then we represent the probability of A into probability of B. Okay, so that's how the conditional independence, the independence works. We can figure it out whether it is true for in this case. We are trying to find out whether the male and the Jurassic Park are actually independent from each other. So in this case, we know that the male and Jurassic Park is 0.3. Okay, and if you try to find the marginal probability of A and B, that is male and Jurassic Park. Okay, marginal probability of male is 0.5. Okay, and the marginal probability of Jurassic Park is 0.4. Okay, so if you try to multiply these two, I don't think it matches this. Okay, so it's 0.2. So we can conclude that these are not independent. Okay, and there is a dependency of a movie and a male. So this also helps us to answer some conditional independence as well. Okay, and there is another way to check it, like probability of A given B. If they are independent, it will be equal to probability of A, which means the probability of someone watching of being a male and Jurassic Park. Okay, if they are independent, it will be equal to the probability of just the male. If we calculate this will not be equal, because we know that there is a dependency in the way people watch movies. So we can conclude that these two variables are not independent by looking at this data. Okay, so this gives an intuition of overall picture of probability and probability distributions and how they're useful. Okay, thank you.